Yes, so hopefully, let me see. Yes, so it is good now. Okay, so good morning, everyone, and let's move on towards our lecture number 6 of physics optional paper 2. Okay, this is basically lecture number 6. Lecture 6. Okay, now before moving on to lecture number 6, I would like to suggest you something that please, if you are watching the paper 1 videos, right? The paper one videos which I have uploaded. So the initial videos are of teachment. Okay, initial videos are from teachment. Okay, and then the upcoming videos. Then some of the videos have been recorded through laptop. Some have been recorded through tablet, and etc. etc. The things are there. Okay, so I would recommend that the paper one, the playlist heading is such that the paper one with playlist heading in bilingual English. Okay, this heading paper one, this your playlist. Okay, uh, if you can bear, if in case you can bear, if you can bear low video quality. Okay, low video quality means the video is not HD over there. Okay, the video over there is not HD because I didn't have the software at that time. Okay, if you can bear low video quality, means 360p. Okay, if you can bear 360p na, 360 pixels, then you should watch this paper one bilingual English, this playlist. Okay, which already some of the students are watching. Okay, if you can bear the low video quality such as 360p or 480p, if you can bear it, then obviously you should watch it. But I am going to relaunch this course in English. Okay, I am going to relaunch this course. Don't worry. Its HD videos are going to come soon. Okay. I am going to relaunch this course and its HD videos are going to come soon. So don't worry. If you still want to see, you can see. Okay. No problem. But the video quality is low over there. And in some of the videos, most importantly, some of the videos there is severe audio and video lag. Okay. Severe audio lag is there in some of the videos. If so, if you can bear it with it, then it's okay. But in case you want good quality videos, then they are going to come now. Now some of the students say that why don't you delete those videos from YouTube? But if I delete those videos from YouTube, then what will happen is that the YouTube has changed its policy. YouTube says that whenever a video is deleted, the corresponding watch minutes are also deleted. Okay, whenever a video is deleted, now the corresponding watch minutes are also deleted. So if I delete the videos, then my watch minutes will be lost. So I don't want that ultimately. So that's why the video let them be like that only. I am going to relaunch that series. So don't worry. Okay, in the HD version like now. Okay, in the high definition, I will upload those. Okay. So let's move on towards our next heading, which is Schrodinger equation. Schrodinger equation. Wave equation for matter waves. Schrodinger equation, which is also called as wave equation for matter waves. Wave equation for matter waves, or fundamental equation of motion of wave mechanics. Okay, it is also the fundamental equation of motion of wave mechanics. Okay, so Schrodinger wave equation is nothing but the wave equation for matter waves, and fundamental equation of motion of wave mechanics. It is also known by these two names. Okay. So what is this basically? If you have watched the playlist, then I have put two videos. Okay. I have put two videos in the playlist. Physics optional paper 2 playlist. If you see, I have put two videos of Rajendra Prasad sir. Okay. Rajendra Prasad sir. I have put two videos of Rajendra Prasad sir, in which there is time dependent and time independent Schrodinger equations are derived over there. Okay. Time dependent Schrodinger wave equation and time independent. Okay. Schrodinger wave equation have been derived in that video, and this is basically your PYQ of UPSC from if you see the 1989 paper, it is asked in 1989, and then after 1989 it has been asked directly in some 2000s. Okay. So very low frequency topic means if you see the derivation, what they ask is in the Schrodinger wave equation, they usually don't ask. Okay. They usually don't ask derivation of time dependent and time independent Schrodinger wave equation. Okay. So usually the time dependent and time independent forms, okay, of Schrodinger wave equation, just derive them. It is not asked. It is generally not asked. But what is asked then? Schrodinger wave equation is a high yield topic, but the thing is derivation is not asked frequently. Okay. They usually don't ask. They may ask sometime. Okay. They may ask sometime, but usually they don't ask. If you see the last 32 years question paper, it is asked, it has been asked only two times. Okay. In the last 32 years, it has been asked only two times. स्क्रॉडिंगर वेव इक्वेशन को डिराइव करो, ये सिर्फ दो बार पूछा गया है पिछले 32 सालों में. ठीक है ना. और उन लोग क्या पूछते हैं, व्हाट डू दे आस्क? दे आस्क द एप्लीकेशन. ओके. its significance, physical significance. Okay. So derivation is not asked usually. Application is asked, significance is asked. Sometimes it's asked to state the equation. Okay. State the equation and explain the terms in it. Okay. And explanation of terms in it. These things are mostly asked, and these things have been asked very frequently. Means if you see the last 32-year question paper, then application, significance, state the equation, explanation, etc. Okay. All things except derivation. Okay. Everything except derivation. Except derivation of time dependent and time independent Schrodinger wave equation. Except the derivation, everything else, whatever is there, it is highly important. Okay. Highly important, because in the past 32 years, not even a single year is there. Not even a single year is there where Schrodinger wave equation has not been asked in one form or the other. It may be asked indirectly. In some of the years, directly it is not asked, but it has been asked indirectly. Okay. So it is a very high yield topic. Okay. The only thing is, they usually don't ask the derivation of time dependent and time independent Schrodinger wave equation. But UPSC is unpredictable exam. Okay. It is unpredictable. It is very much unpredictable exam. So you should be always prepared. Okay. You should be always prepared. And that's why I have put the videos of Rajendra Prasad sir. These are derivations of time dependent Schrodinger wave equation and time independent Schrodinger wave equation. The derivations, I have put two videos in the playlist of Rajendra Prasad sir. So you should definitely watch those videos and make notes out of them, and then you should then come to this video. Okay. So Schrodinger equation. Now the thing is, let me write over here. Then I will explain. Okay. All waves, all waves are characterized. All waves are characterized in terms. All waves are characterized in terms of a wave quantity known as wave function. A wave function a wave function is a function of space and time. Okay. A wave function is a function of space r or xyz. Okay. And time t. Now let me explain this. Okay. So all of the waves which are there in this universe are characterized in terms of wave quantity known as wave function. Okay. Now the wave function, there are two kinds of waves. Okay. There are many kind of wave, like mechanical wave. You know this very well. Okay. Mechanical wave. Mechanical wave. The example is sound wave. Okay. The example is sound wave. Then another example of mechanical wave. What is it? Earthquake, seismic waves. Okay. Let me write seismic waves. Okay. Another example of mechanical wave is seismic waves. Okay. So seismic waves are there, like you must have learnt in your geography, right? Primary wave, secondary wave, relay wave, low wave. All those are basically mechanical waves. Okay. All those are basically mechanical waves because they can be seen actually and felt actually. Okay. Actual vibrations are taking place in it. Okay. Actual vibration of particles is taking place in it. Actual vibration of particles. Then we have something called as electromagnetic wave and etc etc. Okay. Now our focus on in this topic will be on matter wave. Okay. Our focus will be on matter wave in this chapter, quantum mechanics. So our focus is on matter wave. Now the matter wave, every wave has a wave function. These type of mechanical waves also have a wave function. Okay. But the thing is that these wave functions of mechanical waves such as sound wave, seismic wave, in which the actual vibration of particle is taking place, in such waves the wave function is always real. The wave function is always real in these mechanical waves. Okay. But in case of electromagnetic waves and matter waves, the wave function may be real, either real or it may be complex also. Okay. Psi may be real also and psi may be complex also. Okay. The wave function may be real also, or may be complex also in case of matter waves. In case of matter waves, electromagnetic waves, the wave function may be real also, it may be complex also. But in mechanical wave, the wave function is always real only. Okay, always real. Okay. In case of mechanical waves where actual vibration of particle is taking place. Okay. Like in case of sound wave, the sound travels in the form of compressions and rarefactions, right? So it is a real wave, the vibrations of which can be felt clearly. Okay. And seismic waves are also such waves, the vibrations of which can be felt in the form of earthquake. Okay. Primary wave, secondary wave, relay wave, low wave. Okay. So these are basically what? Mechanical waves. So they have real wave function. They have real wave function. But the electromagnetic waves, matter waves, they do not have a real wave function. Okay. So electromagnetic waves and matter waves do not have, means they may have real wave function either, or they may not have. So let me write over here. The matter waves may or may not have psi as real valued function. Okay. So the wave function psi may be real in case of matter waves, or it may be complex. What do you mean by complex? Complex means you must have learned complex numbers in your JE time or your 11th, 12th also. You must have learned complex numbers. What are complex numbers? Square root of negative quantities. Okay. Square root of negative numbers are what? Are basically complex numbers. Okay. Square root of negative numbers are basically complex numbers. Because what happens is that when you multiply minus 4 by minus 4, the result is 16. When you multiply minus 1 by minus 1, the result is 1. When you multiply 1 by 1, the result is again 1. When you multiply 4 by 4, it means you are taking the squares, right? So it is again 16. So I can write that minus 4 square is 16. Okay. Minus 1 square is 1. I can write 1 square is 1. I can write 4 square is equal to 16. Then the problem is that when I take the square root on both the sides, when I take square root on both the sides, then what will happen? Eventually, you are going to get root 16 equal to plus minus 4, right? Root 16 will be equal to plus minus 4, because this is also plus 16 and this is also plus 16. When you take square root on both the side, so plus 16 will have two roots, either plus 4 or minus 4. It will have two roots. Okay. Similarly, square root of 1 will be equal to either minus 1 or plus 1. Okay. So it is like that. But these are what? Real numbers. These are real numbers. These are real numbers. What are real numbers? You have already learnt in the mathematics in the lower classes that real numbers are which type of numbers. Let me tell you. Okay. Root 3 is a real number. Okay. 3 by 4 is a real number. Okay. This is rational number also. You must have learnt all this. Okay. So root 3 is a real number. Root 2 is a real number. Okay. Because it is the square root of a positive quantity. So all these are real numbers. 2 is a real number. Minus 2 is a real number. Minus 1 is a real number. Minus 13 is a real number. Minus 13.67 is a real number. Okay. Minus 7 by 3 is a real number. Minus 7 root 3 divided by 2 is also a real number. Okay. Then what are non-real numbers? What are complex numbers? Complex means imaginary numbers. These are basically such numbers. You already saw this thing that negative quantity squared is also positive, and when positive quantity is squared, its result is also positive. So when negative quantities are squared, the result is positive, and when positive quantities are squared, again the result is positive. So if you take the square root, you are always going to get positive thing inside the square root. Okay. So the thing is, now I am going to define a complex or imaginary number. Why is it imaginary? Why is it imaginary? Because I am imagining. Imagining that some imaginary numbers will be there whose square when I take, it will come out as minus 1. Why they are called as complex or imaginary numbers? Because I am imagining a number. I am basically imagining a number, such a hypothetical number, which is hypothetical. Okay. Hypothetical number means this number do not exist in reality. Okay. So I am imagining such a number whose square when taken, it will be equal to -1. Such a number I am taking. Okay. So do you think such a number ever exists? No, because minus into minus is also plus, plus into plus is also plus. Okay. So square is always positive. So square root should be defined. Square root should be defined only for positive numbers. But I am imagining such a number that when I take the square of it, it comes out to be negative quantity. In other words, I can say that -1 will be equal to plus minus I, and this is called as iota. Okay, so this is basically imaginary number. Okay, it is the square root of negative quantities in short. Okay, so so when I say that the wave function is complex, it it just means that some iota term will be there in it. Iota term means square root of negative number it will be. Not only iota, it may be root 2 iota. Okay, it may be some iota to the power 3 by 2, like that it may be there. Okay, so some psi is complex just means that it will have iota in its expression. Okay, when we write the expression of it in terms of xyz space coordinates and time coordinates, then there will be some iota term which is imaginary number or complex number. Okay, so that is the meaning of psi being real or psi being complex. So for these mechanical waves such as sound waves, seismic waves, etc., where actual vibration of the particles is taking place, the psi value is always going to be real, and that implies that iota will not be there in these when you write the, let me write over here, when you write wave function expression, psi expression for mechanical wave, when you write psi expression for mechanical wave, iota, okay, iota which is equal to square root of -1 term will not be present in it. And this in turn implies that psi is real. Okay, so this is the thing. Now I have explained the meaning of this statement, right? All waves are characterized in terms of a wave quantity. All waves of this world, whether they are mechanical waves, whether they are electromagnetic waves, whether they are matter waves, all kind of waves in this world are characterized, are defined in terms of a wave quantity known as wave function. So even if a wave is there, no matter whether the wave is matter wave type abstract wave, or no matter whether the wave is sound wave like real wave, okay, there is always going to be a wave function associated with that wave. Okay, so wave function is a function of space and time. Okay, space coordinates and time, it is a function of space and time. Now you know this very well, right? R, what is r vector? What is this r vector? R vector is simply x I cap. In Cartesian coordinates, you must have learnt in the vectors of lower classes. Okay, x I cap y plus y j cap plus z k cap. This is the definition of position vector r. Okay, so that's why r or xyz has been written over here. Okay, and time t. Okay, so this is the thing. Now we will write the second property. All functions of space and time do not qualify to to be a valid wave function. Okay, all functions of space and time do not qualify to be a valid wave function. Okay, see, there might be infinite functions of space and time. Okay, there might be, suppose this is the let me take a hypothetical function like this: 3x square plus 4y square plus z to the power 2 by 3 plus 2 by 3 t to the power minus half. Suppose this is my wave function. Suppose hypothetically I am saying, okay. So there are infinite number of such functions, right? There are infinite number of such functions. I can just change this 3 to 4, okay. Even if I change one thing, then it will be another function, okay. That function has changed. Even if I change the single coefficient, or even if I change a single power, even then I am going to get different wave function. So there are a lot of permutation and combination possible. Okay, lot of permutations and combinations are possible, right? So all functions of space and time do not qualify to be a valid wave function. Okay, so if you see a function of r and t, never say that it is a wave function blindly. Okay, we can't tell that it is a wave function blindly. We can't tell. It must satisfy some specific condition so that the wave function is a function of space and time. Okay, and that condition I am telling you now. So all functions of space and time do not qualify to be a valid wave function. Okay, a function of space and time, a function of space and time psi. Okay, a function of space and time psi r comma t, okay, qualifies, okay, a function of space and time, it is represented like this, okay, qualifies to be a wave function, qualifies to be a wave function if it, okay, satisfies the equation, if it satisfies the equation del square psi equal to 1 upon vp square del 2 psi by del t square, okay, which is this equation is known as classical wave equation, okay, where this term is Laplacian, okay, where this term is what, it is basically Laplacian, okay, del 2 by del x square, okay, plus del 2 by del y square, okay, plus del 2 by del z square, okay, this is basically Laplacian, okay, Laplacian, okay, and vp is the phase velocity of the wave, okay, vp is basically phase velocity, of the wave, okay. Now let me explain this, okay. So all functions of space and time are not clearly wave functions, okay. I already told you all functions of space and time do not qualify to be a valid wave function, okay. So a function of space and time, a function of space and time psi r comma t qualifies to be a wave function, okay. this function of r and t psi rt will qualify to be a wave function. Okay, if it, in case if it satisfies the equation this, okay, if it satisfies this equation, then we call that it is a valid wave function. Okay, now what is the meaning of satisfying this equation? This is basically classical wave equation, okay, which you are going to learn in paper 1. Okay, so whenever a wave function satisfies this equation, classical wave equation, then we call that it is basically satisfying the classical wave equation, so it is a valid wave function. Okay, so for a wave function to be valid, it must satisfy this equation. Now what is the meaning of satisfying this equation? Okay, I told this that satisfying this equation. Then what is the meaning of satisfying this equation? Okay, what is the meaning of satisfying this equation? Let me explain you. This is classical wave equation and your psi satisfies this equation, you are saying. Okay, so suppose I have psi equal to some function. Okay, suppose arbitrarily I am taking some function. Okay, 4y square plus 4z square plus 3t cube. Okay, suppose this is my random function. Then what will I do is I will put it over here. I will put it over here. Okay, del 2 by del x square. Okay, plus del 2 means I cap. Okay, and no, not I cap, sorry. Okay, it will be in terms of I cap, j cap, k cap, this thing. Okay, this will be in terms of I cap, j cap. Suppose this is I cap. Okay, suppose this is j cap. Okay, and suppose this is k cap. So what will I do is I will put it in the expression here. Okay, so this question is not asked in UPSC, don't worry. I am explaining that when I say that it satisfies this equation, when I say that it satisfies this equation, what does it mean? I am telling you. Okay, so you will first of all put it over here, and you will find out then you will put psi value from here, this psi value over here. Okay, you will find this value, you get suppose some quantity k1. Okay, you get some quantity k1. Then what will you do is you will substitute this value of psi in the RHS. Okay, you will substitute it in the RHS. Okay, you will substitute it in the RHS. First you substituted it in the LHS. Then when you substituted it in the LHS, you got some k1 quantity, cause k1 constant, suppose. And then you substituted it in the RHS and you got some k2 quantity. Okay, so if you get k1 equal to k2, means LHS equal to RHS. So psi satisfies that equation, that classical wave equation. We say that it satisfies that classical wave equation. Okay, psi satisfies that classical wave equation, and as soon as it satisfies that classical wave equation, I can certainly say that psi is a valid wave function. Okay, psi is a valid wave function. I can say this clearly. Okay, now let me write another statement over there. Okay, now let me write another statement. If it satisfies the equation, this was going on. Okay, then according to de Broglie's hypothesis, this symbol means according to. Okay, this is according to de Broglie's hypothesis. According to de Broglie's hypothesis, a moving a moving material, all moving material particles are associated with concentrated, okay, with concentrated group of waves or wave packet. Concentrated group of waves or wave packet. Okay. So according to de Broglie's hypothesis, all moving material particles, every material particle has a wave associated with it. This is what de Broglie told, right? So according to de Broglie's hypothesis, all moving material particles are associated with concentrated group of waves or wave packet. Okay. So it wants to say is that suppose this is my material particle, then it will have some wave associated with it. Okay. So the particle has a wave associated with it, but this is a very abstract kind of wave, not a mechanical wave. Okay. So it is pictorially represented like this. Okay. And it is a concentrated group of waves or wave packet. Okay. It is a concentrated group of waves or wave packet. Concentrated group means these will be very much near to each other. Okay. It will be basically very near to each other. Such a manner it will be. Okay. So these are going to be very concentrated waves. That's what it says. Okay. Concentrated. Okay. So concentrated group of waves or wave packet. So all material particles are associated with concentrated group of waves or wave packet, and this is what is called as wave packet. Single unit is called as wave packet. This is a single packet. Okay. This is another packet. This is another packet, and there will be many such packets. Okay. And the particle always lies within this packet. This is the packet. Suppose then the particle can lie anywhere in this packet. Okay. Such is the hypothesis. It is not necessary that the particle will lie at the center of the packet. It is not necessary. It can lie anywhere in the packet. Okay. The particle can lie anywhere within this packet. Okay. So it is basically we can't determine the exact position of the particle. It may be anywhere within this packet. Okay. So concentrated group of waves or wave packet. Okay. Such matter waves will also be described. Okay. Let me write over here. So it is obvious na. Such matter waves will also be described in terms of a wave function. Okay. So let me write such matter waves will also be described. Such matter waves will also be described in terms of a wave function. Psi, okay, r comma t. Okay. So such matter waves which are de Broglie waves will also be described. I already told you na that all types of waves have a wave function with them. Okay. No matter whether the wave is, I already told you, see over here. Okay. All waves are characterized. I had already told you this. All waves are characterized in terms of a wave quantity known as wave function. Okay. So all waves are characterized in terms of a wave quantity known as wave function. Then it is obvious that it is written that all waves are characterized. Then what is wrong with the matter wave? matter wave will also be characterized by a wave function. Okay, so such matter waves will also be described in terms of a wave function psi r comma t. Okay, then I will write in the next slide. Okay, introducing the idea of de Broglie hypothesis. Introducing the idea of de Broglie hypothesis in classical wave equation. Introducing the idea of de Broglie hypothesis in classical wave equation. Okay, so de Broglie's hypothesis. What is de Broglie's hypothesis? Every material particle has a wave associated with it. Okay, so what did Schrodinger do basically? Okay, so introducing the idea of de Broglie's hypothesis in classical wave equation, Schrodinger obtained wave equation for material particles in non-relativistic motion. Okay, in non-relativistic motion. Okay, when the property spin of the particle, when the property spin of the particle is not taken into account. Okay, so what did Schrodinger do basically? He introduced the idea of de Broglie hypothesis that every particle has a wave associated with it. Okay, so what did he do? He put the value of psi, matter wave psi, in the classical wave equation. Okay, he put the value of psi in this equation, classical wave equation. Okay, and after putting the value of psi in this classical wave equation for material particles, okay, he obtained the Schrodinger wave equation. But the thing is that he he did so for non-relativistic motion. Okay, this is a very important point. Schrodinger wave equation is applicable only in non-relativistic motion. Okay, Schrodinger wave equation is applicable only in non-relativistic motion, and that too when the spin of the particle is not taken into account. Okay, this is a very important fact. So let us write in the next slide. Okay, let me write over here. Schrodinger wave equation is applicable only when, okay, Schrodinger wave equation is applicable only when the motion of the material particle is non-relativistic and when spin of the particle is not taken into when spin of the particle is not taken into account. Okay, so only in this situation the Schrodinger wave equation will be applicable. Okay, so what is the Schrodinger time dependent equation? Then I will tell you now. Okay, let us write Schrodinger time dependent equation. Okay, so let us write over here Schrodinger time dependent equation. Okay, derivation derivation of it has already been provided on. So its derivation of Schrodinger time dependent equation has already been provided on Telegram. Okay, so you can certainly watch that from there. Okay, in the form of video lecture of some other person. Okay, one of the teachers, Rajendra Prasad sir. Okay, so राजेंद्र प्रसाद सर उनके वीडियो डाल दिए हैं मैंने टेलीग्राम पे. ठीक है, आई हैव पुट हिज वीडियोस ऑन टेलीग्राम, and in those videos of Rajendra Prasad sir it has been derived, so you can definitely watch it, and you can also make the notes from there. Okay, so derivation of it has already been provided on Telegram, and now we are only going to look at the significance. Okay, now how is it represented? Schrodinger equation. Okay, it is represented like this. Okay, R comma T. Okay, this is basically time dependent equation. Why is it time dependent equation? Let me write over here. When psi, okay, is a function, when psi is a function of R only, then it is time dependent Schrodinger wave equation. Okay, when psi is a function of R only, not T. Okay, when T is absent in the wave function psi, whenever T is absent in the wave function psi and it is only a function of R, that is the position coordinate. So whenever psi is a function of only position coordinate, then surely it is time independent Schrodinger wave equation. And when psi is a function of R and T both, when psi is a function of R and T both, okay, when psi is a function of R and T both, it is time dependent. It is time dependent Schrodinger wave equation. It is a common sense, na? When look at here, when I say that psi is a function of psi of R, only R, okay, then definitely there is no T term present in it. Okay, so when I write the function, I will write simply 3x square I cap plus 3y square j cap. Okay, like that. Means this is not an example of function, but I am just giving you an blur idea. Okay, so suppose this is a function. Okay, suppose this is a function. So over here no t term is present, no t term, no t term. As no time term is there, this is clearly time independent. Okay, time independent. So time independent means over here the power of t will be 0. Okay, if you say time independent, then the power of t will be 0, and t to the power 0 means anything to the power 0 is always 1. Okay, so basically t power is 0 in time independent Schrodinger wave equation. So as t power is 0, any variable to the power 0 is always 1. So this term will be ultimately 1. So in t to the power 0, whatever you put doesn't matter. T equal to 1 you put, t equal to 2 you put. Okay, not 1. 1 will not be allowed. 1 to the power 0 is not defined. But suppose t equal to 2, t equal to 3, like that. Okay, so there is no time term, means time to the power 0 can be considered, or time term is itself absent. Okay, so it is time independent basically. Okay, and what is time dependent one? This is the time independent. So this is the function. Now time dependent example I can give you like this. Okay, I can give the time dependent example like this. Okay, suppose this is the function. Okay, 3x square t square I cap. Okay, plus 3y square t cube j cap. Okay, plus 3z square t to the power 4 k cap. Okay, so this is what you have the t term. Okay, you have t term over here. So it is time dependent. This was time independent. Now this will be time dependent. Why? Because value with change with time dependent. Why dependent on time? Time dependent on time because time term is there clearly. Time term is there. You can see time term is there over here. Time term is there over here. Time term is there over here. So this is what time dependent. And in the previous one, there was no time term present. Only x, y, and z were present. No t was present. So it is time independent because even if you put different values of t, there is no t term present over here. Okay, so for t equal to 1 also, this function will be unchanged. If you put t equal to 1, then as there is no t term over here in this function, so clearly its value will not change. For t equal to 2 second, its value is going to be the same. So it is time independent, independent of time. Whether the time is 1, whether the time is 2, doesn't matter. It is independent of time. And over here, time dependent means if you put time t equal to 1, I am going to get 6x square, not 6x square. You put you put time t equal to 1 over here. So you will get 3x square plus 3y square j cap. Okay. So the function will change. If you put t equal to 2, then this will be basically 12x square I cap plus and so on and so forth. So it is clearly time dependent, as if you put the different values of t, if you put different values of t, you are going to get different values of psi. So this is time dependent. Okay. So t has some finite power. Okay, or and over here the power of t was either 0 or t term was not at all present. Okay, either the power of t was 0 or t term was not at all present. So this is what, this is basically time independent equation, Schrodinger wave equation. Okay, because it is not depending on time. Okay, so this is the thing. Now the equation can be written in the form. Okay, the equation can be written in this form, like the equation can be written in this form: h okay r comma t, okay, which is equal to e psi, okay, r comma t. Okay, So this is basically the form of Schrodinger wave time independent, time dependent equation. Okay. Form of Schrodinger time dependent. So this is in this form the Schrodinger time dependent equation is written. And what are these over here? What are these? Basically, you have written h psi r comma t equal to e psi r comma t. Okay. So what are these terms h and e over here? Okay. Let this be equation number one for the time being. So here h is equal to what is it? Hamiltonian. Hamiltonian. Hamiltonian operator. It is basically Hamiltonian operator. Okay. And E total energy of the particular system. Okay. E is what? Total energy of the particle. Or so E is the total energy of the particle or system, and H is the Hamiltonian operator. Okay. So in this form, Schrodinger time dependent equation is written. Okay. Now we will learn about operators in the upcoming classes. We are sure to learn about operators in the upcoming classes, no doubt about it. But before that, let me have some water so that I feel comfortable. Okay. Let me have some water so that I feel comfortable. Yes, so I had my water. Okay. Now let's move on towards the further topics. Okay, so H is basically Hamiltonian operator. You will learn about the operators in detail in the upcoming classes. But for the time being, accept the things as it is. Okay, for the time being, accept them as it is. Okay, so E is the total energy of the particular system. Okay, E is total energy of the particular system. H is Hamiltonian operator. Okay, now classical Hamiltonian. What is classical Hamiltonian basically? Classical Hamiltonian operator is like this. Okay. You will learn about this in the upcoming classes in detail. But for the time being, accept these things as it is. Okay. Now classical Hamiltonian. Okay. Classical Hamiltonian. Hamiltonian. Okay. H equal to T plus V. Okay. Classical Hamiltonian. Where T is the kinetic energy. Okay. T is kinetic energy and V is your potential energy. Okay. Quantum mechanical Hamiltonian or Hamiltonian. Okay. Yes. So either you can call it Hamiltonian or you can call it Hamiltonian operator. Both will mean the same. Okay. Either you call it Hamiltonian or Hamiltonian operator. Both are going to mean the same. Okay. So quantum mechanical. Quantum mechanical. Quantum mechanical Hamiltonian. Quantum mechanical Hamiltonian, or you can or else call it Hamiltonian operator. Is given as Okay, how is it given? It is defined like this. Okay, just remember these things for the time being. You will learn these things in detail in the upcoming classes, so you don't have to worry about it. Okay, up to now everything is good. So yes, so over here, okay, I hope that you are noting everything. Okay, h square by 2m, right? Gamma square. This is basically your kinetic energy operator. Okay, K operator. Okay, potential energy and operator both are same. The potential energy is itself an operator. Okay, operator, and I h cut del by del t, it is basically total energy operator. Okay, total energy operator. So over here you can see this thing, an energy operator. Okay, uh, let me write over here, E equal to I h cut, okay, del by del t. It is basically your energy operator. Okay, so 3D time dependent, 3D time dependent. Okay, Schrodinger equation is given as 3D time dependent Schrodinger equation is given as minus h cut square divided by 2m del square plus v r psi of rt. Okay, this is basically like this. Okay, equal to I h cut del by del t. Okay, psi r comma t. Okay, let this be equation number one. Assume this to be equation number one. Okay, let this be equation number one. Then obviously, if we take the one dimensional equivalent of it, this is basically what, three dimensional, right? This is three dimensional. Why is it three dimensional? Why is it three dimensional? Because you can clearly see this, that in the Laplacian three terms are going to come. Three terms are going to come in the Laplacian. In the Laplacian operator, three terms are going to come, and these three terms are basically your what? These denote basically Laplacian. Okay, so these terms they denote Laplacian. Okay, so now it's one dimensional equivalent. How will you give its one dimensional equivalent? See, if the motion is in three dimension, if the motion is suppose in three dimension, suppose the motion is in three dimension, that is the x along x axis, along y axis, and along z axis. If the motion is along three dimension, then you clearly can see this thing, that it will occupy some volume. Okay, but if the motion is in one dimension, okay, if the motion is only in one dimension, and these two perpendicular directions are restricted, these two perpendicular directions are restricted, this direction is restricted and this direction is restricted, then suppose that it is moving only along the x direction, then the equation will change. What will change in the equation? This del 2 by del y square term will vanish. Del 2 by del z square term will vanish. Laplacian will only be equal to this for a one dimensional motion. Okay, so it is not written as Laplacian then. It is simply called del 2 by del x square. Okay, Laplacian is called until when x, y, z all the three are present, then it is called as Laplacian. But as soon as we are constrained in one dimension, as soon as we are constrained in one direction, the y and z terms vanish and only x term remains. So it is no longer called a Laplacian then. It is simply called del 2 by del x square then. Okay, so one dimensional equivalent can be written as, let me write over here. Okay, so one dimensional equivalent is given as, it's, okay, one dimensional, it's one dimensional equivalent, its one dimensional equivalent is given as, okay, minus h cut square over 2m. Okay, and here it was what? Here it was Laplacian square. Okay, means not Laplacian square, we should not call it Laplacian square, it was del square. Del square means Laplacian. Okay, so now uh, y and z terms vanish, so only x term remains. We are assuming that the motion is taking place only along x direction. So your potential energy, which was a function of position vector r, now the position vector r has been restricted. Okay, and the position vector r, as it has been restricted, so it will be v of x, because you only tell me. So it will be v of x. Why it will be v of x? Let me tell you. If you are talking about motion in all the three directions, then your r vector will be something like this. Okay, your r vector will be something like this. Okay, but when you restrict the motion in one dimension, you simply you are left with this, only x term you are left with. Okay, so instead of calling v of r, if the motion is three dimensional, I will call it v of r, means function of r, means position vector. But when we restrict it to one dimension, when this term becomes 0, this term becomes 0, because in one dimension y equal to 0 and z equal to 0, because motion is only along x direction. So ultimately v of r will become vx. Okay, so that's why it has become now vx. Okay, and as it has become vx now, so now here will be, okay, psi x comma t, okay, equal to, it will not change, this will not change. Okay, this will not change, this will it has also changed. You can see that r comma t, instead of r comma t we will have x comma t, because we are constrained in motion. Okay, we are constrained in motion, so instead of r, this complete r, again it will be x. Okay, so here also instead of r, instead of r vector I have put x over here. And why I haven't put the vector sign? Why have I left the vector sign? Because in one dimension you need not specify I cap, j cap, k cap. In one dimension there is no need to specify I cap, j cap, k cap. You can simply write it as, you can simply write this r vector equal to x I cap, you can simply write it as equal to r equal to x. You can simply write like that. Okay, so I can remove the vector sign and put x over there. So that's why instead of this term, instead of this term, I am putting uh, x over here. Okay, so I have put x over here. Then we have equal to I h cut. Okay, del by del t. Okay, psi x comma t. Okay, so let this be again the same thing, right? So now the let this be equation number 2. Okay, let this be equation number 2. So this is basically one dimensional equivalent of time dependent. Okay, this was basically what? One dimensional equivalent of time. Let me write over here. one dimensional equivalent, one dimensional equivalent, one dimensional equivalent of Schrodinger time dependent equation, one dimensional equivalent of Schrodinger time dependent equation is like this, that it will be h cut square divided by 2m del 2 by, again I am writing just for your sake of convenience, okay, just for revision purpose we are writing like this, okay, x comma t, okay, equal to I h cut del by del t psi comma, okay. This is the one dimensional equivalent. And what is the three dimensional one? The three dimensional one is very clear, 3D time, three dimensional time dependent Schrodinger equation, okay. You must mug up these equations, okay. So three dimensional time dependent Schrodinger equation is basically your this thing, okay, 2m, okay, uh, this thing plus v r, right, psi, okay, r comma t, right. Then you have I h cut del y del t, right, psi r comma t. So this is your 3D time dependent Schrodinger equation, and it is its one dimensional equivalent, okay. So this is its one dimensional equivalent, and instead of r you will put x everywhere, okay. Everywhere here there is r, right. Here there is r, here there is r, here there is r, and in its place you will put basically x, x and x, okay. And Laplacian will reduce to del 2 by del x square, okay. Laplacian which is given as like this, okay, Laplacian which is given like this will reduce to del 2 by del x square for one dimension. It won't remain, all the three terms won't remain in it, okay. It will reduce to this, okay. So this is the thing, right. Now we will move on towards time independent Schrodinger equation or steady state form of Schrodinger equation, okay. Now we will move on towards time independent form of Schrodinger equation.